Yo, what's up, welcome back. Today we're working on my operating system. It's a x86 operating system written in Rust. And what we're working on today is trying to get USB support working. So just like a quick little project recap, where are we at right now? Hold on, let's just clear out some shit. I have this like project that I can build and I can run. It like makes a little boot ISO and starts up this like virtual machine, QEMU, and starts running my OS. And what can it do right now? It boots, it has like memory allocation, so somewhere we have like logs proving that we have like vectors and maps. We have concurrency, so right now I'm like running this like bouncing ball demo, but if I open up a browser window and I go to like the stream OS IP, I have like a web server running at the same time. It's doing both of those at once. Great. It has like serial support and like a log infrastructure, so when I run QEMU, it like takes the output of the serial console and it forwards it to standard input output, which lets me like read logs. Great. It has unit testing, so if I run cargo test, it boots up this like second kernel that runs the operating system in this like special mode. Blah blah blah. Runs these unit tests and like flags these like test failure to the parent system. Very cool. We have like clock support. Our like web stack works to some extent, which means we have like an Ethernet driver, like PCI, ARP, UDP, TCP, HTTP, all of that stuff looking good. And we have like graphics in keyboard, and like recently we just finished multi-core support. And what we're working on today is we're trying to implement USB support in order to try to get like some form of mouse input through like the QEMU's like USB tablet, so that we can eventually tell this guy on the internet who said my OS couldn't run Doom that he's wrong, right? That's the end goal here. End goal, intermediate goal. Yo. So yeah, that's what we're working on. And where we got to yesterday was we had kind of got to the point where we had like a USB controller, and we could kind of, how do I say this? We found the USB controller, the UHCI host controller. So that's this guy. And kind of, let's see if I can find like the Intel specification on UHCI, because that's easier to look at. And if I understand kind of like the current, like, well, my current understanding of USB is kind of something like this. I got my like CPU. This is me. And he's connected to a PCI bus. PCI. On this PCI bus is like a USB controller. USB host. This guy, he's got like some like USB ports on him. And like you can like plug in a USB thing to this, like my like keyboard or mouse, right? And so what I'm supposed to do is I'm supposed to talk to this guy. He's kind of like mapped into like memory as well. So I think I have like memory over here, mem. And like this guy kind of like also connects to memory directly, or maybe it's more like the PCR card. It talks to memory and he maps some stuff in there. I'm not quite sure. And what we've kind of got to yesterday is we were looking at like UHCI, which is like extended host something, enhanced host controller interface. And that's the like USB 2.0 way of talking to devices. And we got like to the point where we could talk to the card, but we don't really know like what we're supposed to do. And I was doing some like reading, and eventually I think it's in here. Basically, I was trying to like skip some of this like UHCI stuff, i.e. USB 1.0. And after doing some reading, I think that it's quite USB is already quite complex. Like a few reasons. One, USB complex. Two, the goal of like putting in mouse support. Actually, if I look at like the QEMU docs, they're like USB tablet, which is like the thing that you pretend your mouse is. They connect via UHCI, not EHCI. So like the easiest way, blah, blah, blah. QEMU will create the UHCI controller function of the PX3 chipset. It will carry this name. And somewhere they say like here, basically, they're saying like when you create the USB tablet, you put it on the UHCI bus. So I was trying to kind of skip USB 1.0 and go straight to 2.0 because in my mind that's like what normal mice would implement. But it seems like QEMU is saying that they would, like, their recommendation here is to stick it on 1.0. So I might as well stick it on 1.0. Reason 3 that I want to change directions is that it's just easier. UHCI just seems easier. So I think what I want to do today is pivot a little bit. Look at UHCI instead of EHCI. Luckily for us, we didn't make much progress on EHCI. And maybe if we get to the point where our UHCI stuff is working well, then we can look at EHCI, i.e. USB 2.0 for faster speeds later. So that's kind of what I want to look at today. And like, I don't really have like a good goal in mind because I'm pretty lost still in terms of like how much work this whole feature is going to be. The USB spec looks like pretty complex. And so I think that like all I want to do is make some form of progress on USB in general. So that's what we're looking at today. Yeah. So I guess the first thing that we want to do is like enable UHCI controller and find it. Right, because like that's kind of what we did last stream, was we enabled the EHCI controller, we found it, but I haven't really seen the UHCI one. So if I look at UHCI on the OS Dev Wiki, let's see, they claim that they define a set of registers for USB that are connected to a PCI controller with a class ID C, subclass ID 3, and interface value 0. So that should be really similar to what we had for EHCI. Let's see if I can find this. So what we did last stream is we kind of like iterated the PCI device space, and we found one that had a class ID of 0xC, subclass ID 0x3, but interface value, I think 20. Yeah, 0x20. And so I think we should be able to just find one with this interface ID 0 if we set up QEMU right. So our QEMU command line flags, he sets up this like USB thing, which I think if I read the docs correctly, they're saying that that should create a UHCI controller. Great. So if I run and I look at what PCI devices we've found, it's odd that I don't actually see any with that subclass. I'm getting there quickly because I kind of cheated before and I looked at this earlier. So I see class 12, subclass 3, interface 32, but I don't see class 12, subclass 3, interface 0, which is like pretty fucking weird. And so I was like doing some like QEMU flag experimentation off screen. And basically what I found is if I type in like device, Pix 3 USB UHCI, I think that's a valid device. Right, and then I say, please go onto bus PCI 0. So I explicitly say, like, put me on this PCI bus. Then I find it. Hold on, let's see if I can. 1230, right here, 1230. We're seeing bus 0, slot 5, 1230, which is what we're looking for. But if I don't specify a bus, I think I don't. Oh, I do see it, 1230. But I don't understand why, like, they're saying that this USB option, this should add one as well. Right, if I just say, oops, where am I? Delete this flag. One, it's saying that, like, I can't add my USB tablet because it can't find the bus. But also, I don't see anything go away. It's very, very confusing. And so that's what I wanted to look at is, like, see if I'm missing something with the default USB initialization, and see if I'm like missing something there. So also pre-stream, I was looking at like the QEMU source code a little bit. And I was looking for this like PIX, what is it? It's, okay, first of all, what am I talking about? When I add this like dash USB, they say that they enable this PIX3 thing by default. Let me see if I can find it. Yeah, so here they're saying that when I add the dash USB switch to QEMU, it enables a UHCI controller as a function of the PIX3 chipset. So I'm like, what the fuck's a PIX3? And here we go. This is probably what it's talking about. And it is a Southbridge thing connected to the Intel CPU. So they're basically saying like, we've like bundled a bunch of features related to like IO and stuff. So like interrupts, PCI, all of that goes through this like this guy here. And so I'm wondering if like I've missed something about how to interact with this thing. This like spec is kind of indicating that it should be connected via PCI, but then how come I don't see it by default? And so I was looking at the QEMU source code, and I was looking at like PIX3, USB, UHCI, this guy. And I'm like, where the fuck is this used? PIX3, USB, UHCI. And I see like this table, and they're talking about how they're like putting stuff at specific addresses. And I noticed something kind of odd here, where they're talking about they're like commenting in PCI IDs. Sure, whatever, I don't care. But then I was like, wait a second, what the fuck are these PCI IDs? Because I've seen these before, where if I look at like, my Linux OS, I go like sys class PCI or devices maybe. Like I have these devices sitting around at these things. I'm like, what are these supposed to mean? And if I look at like PCI address format, there's this bus device function. And here's where I start to get like really fucking confused, right? Because last stream we noticed that we were iterating over device numbers from 0 to 255. And we were hitting problems where we were overflowing. And we were what is the reason for this? It was because like there's only 32 bits. And for a second, until just like 2 seconds ago, I thought that 1D was more than 32 bits, but I think it's not actually. I think if I like Python and I format or print 0x1f, that's 31. Okay, so if I have like a thing at 0x1d, which is what they're claiming it should be at, I think, in the QEMU source code, is that what I saw? USB UHCI here. 001D 0. I thought for a second, like, maybe I'm not seeing that. I'm also noticing that I never iterated functions. So here they're saying that there's BDF notation, which is like bus device function. And I'm just only ever looking at function 0. So it could be that like this like PIX3 chipset maybe is like a PCI device that is multifunction, and one of those functions is USB, and I'm just not looking at it. So I did want to look at that. That's my first guess as to why I'm not seeing this like USB device when I specify USB this way with just like the USB flag in QEMU. So how do I find that? I guess I would go into my PCI device iteration stuff. And here, one thing I also noticed actually is that I'm getting a duplicate still because I'm looking at slot 32, which is just invalid. I should be only looking up to slot 31, so we'll fix that here. And we're also going to start iterating function numbers. So here we can say this increment stuff is we're going to first iterate function, then iterate device, then iterate bus. So we'll say self function equals self.function plus 1, and then we're going to mod that by by what? How many bits does the function allow? How many bits? So here we have function number is 3 bits, so maximum 8. Self.device num is equal to self.device num plus 1. But this is mod 32. And the device num, and now we're going to do bus num. And we have 255 potential buses. And then for each one of these, we're going to say if we've wrapped around, if we haven't wrapped around, we break. We say we're done. So this is device num, and this is bus num. And so this should ensure that we iterate first by function, then by device, then by bus. And then if we get through all of those, and all 3 are equal to 0, then we have finished iterating. And then here, I just need to make sure that I'm passing in the function number when I'm doing my reading. And now we should be iterating all functions as well. I just have to make sure that I initialize the function to 0. And now I'm seeing a problem here where I'm like duplicating something. So I think device already in use. Right, because my allocated devices, he doesn't actually store the function here. So we just have to do this, and here we have to say self.function. And I think that's it. Config read everywhere. He's got some hard-coded zeros in here, so we'll just throw in self-function here. This guy should also be self-function, except it's adder.function, not... He's got a nested thing inside. Okay. And where else do we read the PCI space? Everyone seems to be using the function now, so if I run this, he's mad at line 61. Why? Because I didn't pass the function around, so self.function, great. We propagate, we propagate, we propagate. And it looks like everything we find is function 0. Which is kind of surprising. I was kind of hoping that would be it. I wonder if maybe it would be good just to make sure that I'm... maybe I log in here. And I'll say bus this, slot this, function this, offset this. Just to make sure that I'm reading what I expect to read. You know? Oops, and of course I need to punch in the things I want to print, like an idiot. I just didn't. Oh, and of course this is going to cause problems because we are printing way too much before we are able to service our logs. Okay. So we are seeing ourselves just ripping through every bus slot function. I guess this is annoying because this printing is just taking like a fucking year. Yo, what's up? And I only want to see like later to make sure that I'm doing this, but I guess we are getting indication that we are looping over all bus slots and functions. And then here, when we're pulling class IDs, we're only looking at function 0. So it looks like every time we like checked to see if we had a thing available, we only ever saw something at function 0, which is interesting. So I was kind of hoping that we would find a multifunction device and we'd find a UHCI controller there. But we're not. So what is the next guess? I guess the other thing I want to know is like, what are these things that we're finding? So I wonder if there's like a way for us to look if there's like a little extra metadata in the PCI stuff. Maybe. Oh, I'm only logging general PCI devices. But it could be that like if I remember correctly, there are like bridge types, and so let's like double check to see if we're getting any bridges. So here we can just say if we get something that's not a general device. So we'll say PCI. I guess we'll like get a thing, and I guess we'll log the thing and still filter it out. Let's see what we get. Oh my god. So let's turn off that fucking logging. PCI. Just delete this. Do we see anything? No, so it does look like that we are only ever seeing general PCI devices. So no bus expanders or bridges or anything. And maybe it would be interesting to see what these are. So 1237, what is that? This is an Intel 82441. What the hell is that? This is the i440FX. Okay. Which I think is I think I read somewhere. This is just what the fuck is this? Host PCI bridge and PIX3 PCI to ISA bridge. Yeah, so this is related. Somewhat to what we're looking at. And then what was the other thing we saw in there? We also saw this guy, 0x24CD. This is the USB UHCI card. This is the RTL 8139. So this is our network card, and the only thing we're missing is like 0x12341111. What's that? So I don't know how to find this. Maybe I look for like end of line. So here it's a QEMU thing. And oh, this is like the QEMU VGA card. 12341111. Okay. So I guess like if I look at QEMU docs, they do say that they connect the UHCI controller as a function of the PIX3 chipset. And they're also saying that the i44 whatever OX is like a connector to that guy. So maybe I do need to interact with that thing in some way. Like, what if I just like look this up? Okay. So this is like this guy sees that he's seeing brute force enumeration. Wants to see, he's looked at info Q tree in his QEMU console. Oh, okay. That's an interesting piece of info that we can try. So I think it's like Control A, C, Control A, C, Control A, X. How do I get out? Like I want to see the QEMU console. Which is through QEMU console hotkey. What is the short for it? Control A and then press C. I was pressing Control A then Control C. No. Am I? Oh my god. So this is getting like extra complicated because my QEMU, my like TMUX bind is also Control A. So I think I do Control A, then press A. No. Control A, press Control A again. Then C. Nothing. Oh my god. Console. Qt provides a monitor that allows host system users to control the enemy get system. To open the console, press Control A. I'm missing something. If you want to terminate, then press Control A, press X. I think I've actually seen that if I see no graphic, this stuff seems to work differently. Let's just try that again. Yeah, here we go. Now I have the console, which is kind of weird. Okay, anyways, this guy says info Qtree. And what we're looking for in here is like any indication that somebody is the USB thing. So we have USB UHCI, RTL8139. Then we have this PIX USB UHCI, great. He's got an address of 012. Okay, wait. That's interesting. So he has an address of 01.2. So we know that at bus 0, device number 1, address 2, we should fucking find this thing. And so now the question is, why not? Because we should find this vendor 8086 7020. Interesting. So why aren't we finding that? We must not be iterating functions correctly. But that's nice though. That means that my guess that I wasn't looking at the right function was like correct. So that's pretty fucking cool. I was kind of expecting that to not be. Okay, so how do I validate this? Let's look at our config read. We say, here I have a bus, a slot, a function, and an offset. And I'd like to select this PCI address, please. And here I write bits 8, 9, and 10 with the function of this request, of this address. Which is correct. Function number should be 8, 9, and 10. Device number should be 11 through 15. Which is correct. So why the fuck not? Maybe here we should print the function address that we're reading. And only in the case where we have bus slot function what we expect now. Because now we know what it should be, right? We know that we should have bus is equal to 0. Slot is equal to 1. And function is equal to 2. I think that's what we saw, right? Here we saw bus, adder is, or slot 1, function 2. Yep, okay. And so we'll just say, in this case, let's print what we wrote. So here we print out the address that we're selecting. Okay, so we are writing out this. In the case where bus is 0, slot is bus 0, slot 1, function 2. Which means that here we should, this number is A. So we'll just print that as binary, I guess. So we say format, no. We say, I want to put a string here. Format is Boolean. And let's throw an A in there. So we get function number. Yeah, this lines up, right? So this 8 bits are being shown as the function number is 010, which is 2, and the device number is 1. So all of this is like lining up. And so then the question becomes, why the fuck is my function number not working correctly? Oh, hold on. Because this isn't how you do it. Oh, okay, sorry. Okay. How do I explain this? I think somewhere when I read each PCI device, I think I don't have to iterate functions like this. I actually didn't. I should just read this. Multifunction devices. They behave in the same manner as normal PCI devices. The easiest way to detect a multifunction device is bit 7 of the header type field. If the device is, it will have this value set if it's multifunction. Unused functions have vendors 0xFFFF. Make sure you mask this bit when you determine header type to detect the number of functions. You need to scan the PCI configuration space for every function. Functions are not necessarily in order. You can have functions 0x1, 0, 1, and 7. Okay, so they are claiming that if I scan the functions, I should get vendor IDs back. Unused functions have vendor 0xFFFF. So somewhere I have that checked. In my like device iteration, I see if my vendor is 0xFF, fuck off, is essentially what I say here. So maybe let's it's possible that I've like reversed this in some way. So let's just double check that I'm not off by like maybe I'm reading like not reading the vendor correctly. I guess let's say if we'll do the same thing where we'll say if this bus num is equal to 0 and the device num is equal to 1 and the function is equal to 2, that's what we expect to be like the right thing. We'll just print line, or we'll say info retrieved vendor bits is equal to device vendor. Let's just see what we get. We'll run, we'll look. That's interesting. We do see 8086-7020. Okay. So why the fuck is this getting skipped? Why aren't we returning that? Hello? Hold on, hold on. What am I missing? What the fuck? So how come I'm never seeing that logged? Okay, so... Oh, fuck me. So I just missed these, like, config read? I missed one. Oh my god, there's a hard-coded 0 in here. Fuck me, dude. Okay, is there anywhere else that I've fucked that up? I think they're all set. And then config rights, do I have them all set here? No. This guy needs a self function. This guy needs a self function. All right, let's try that again. That's so annoying. Okay. Oh, God, was that a fucking nightmare? Okay, so we've found the UHCI controller now, right? If we, hold on, let's run this with graphics enabled. I think that fixes something. Why am I not seeing... am I not supposed to be seeing the class IDs as well? Oh, here we go. This is what I'm missing. So now we have on bus 0, slot 1, function 2. We found class 12, subclass 3, interface 0. So that's our UHCI controller. And it just took us like a fucking year to find it because we weren't iterating functions correctly. Where functions is like this PCI card has multiple things in it. Oh man, what a saga. Okay. Cool. So we found it. We found it. Which means that we can start looking at UHCI. So let's say that the next milestone that we want is like interact with UHCI controller in some way. Okay. So let's, I guess, cargo format, cargo Clippy, just make sure that like everything's in order. And we have a clear chunk of work, which is fixing or like iterating functions. So we won't add this stuff, but we'll add this. All of this stuff is needed. All of this stuff is part of it. We don't add this, we don't add this, we don't add this, we don't add this, we don't add this. And we'll just say fix, we'll say git commit PCI function, or iterate functions, PCI functions in addition to buses and devices. And we also say bonus fix device iteration stops at 31 instead of 32. There we go. There we go. God, that's annoying. So I think everything else we've changed so far, we can just kind of like get rid of. I think. Oops, we do have some like formatting issues as well, but that's okay. These aren't related to what we just changed. And in main, now instead of looking for the EHCI device, i.e. USB 2.0, we can look for the UHCI device. So I think all we have to do here is we'll change these to use. This is a UHCI, this is a UHCI, this is no longer interface ID 20, this is interface ID 0. We change all of these guys to use. And in the kernel, we save a UHCI instead of an EHCI. We change our module name to UHCI. This guy goes to UHCI, and this is UHCI instead of an EHCI thing. Just change everything around the board. There we go. Now we go to source, and we move EHCIRS to UHCIRS. Okay. Cool. And in our UHCI file, we change this to a U everywhere. What a pain. Okay. Well, if only there was a cargo thing for C++. Is the only reason I'm getting into Rust. Dude, C++ dependency management is the fucking worst. I don't know if that's what you mean by cargo or if you mean that their like compiler errors are way better, because also C++ compiler errors are the fucking worst. Holy shit. Yeah. They're both awful. And yeah, dude, the Rust compiler, its complaints, I think it's like what C++ complains about is like reasonable. And so they just kind of like dump their error and they're like, you did a reasonable problem, figure it out. And that's like one type of hell. But in Rust, like they kind of, to get adoption, needed to, like, if their compilers were nearly as bad as like C++'s, no one would ever fucking used it, right? Because you'd have like some like borrow checker error, and it would be like, oh, here, like if they did like the template thing and they like dropped out like 400 lines of code, you would just be like, fuck this language, I'm out. Fuck this. But yeah, instead, they made their compiler very nice, which makes it actually kind of nice to work with, despite the pain in the language itself, which is kind of funny. Yeah, template errors, I think, is like finding the template error quickly is like an art. Like you actually, like you have like 400 lines of output being like, I tried every single thing that I could possibly think of, and you have to like figure out like what that actually says. Ugh, what a pain in the ass. What a pain. Anyways, enough ranting with C++. Actually, C++ is actually great. It's got its problems, but it's got its pros as well. Okay, so what am I doing with this UHCI thing? Before I was reading these like specific things in UHCI space, and I guess let's do what we did last time, and we'll see if we can find some proof that we've got like the right IO registers. So I guess let's just Google this PDF really quick and see if like there's something similar where what we did last time is we like looked at the initial state of the IO registers, or sorry, of like the command registers and stuff like that in the USB controller for UHCI, and we were like, did we find what we expected to find? And so let's do the same thing here, where maybe we can find like an initial state and see if it like makes sense. Okay, so in here, do they have like default values? So they do have default values for all of their registers. And so I guess what we do is we just iterate over all of their registers and see if we get the defaults. Let's do that. So this is for UHCI. Here are their IO registers at these offsets. So we can just do this. We could do some like Vim bullshit where I delete all this shit and I just paste this in. And what is this going to look like? It's like PCI dot self.device dot register. What is like, I can't remember my API on here already. This guy has a, oh, he gets the mmap range. Right. So I actually should have left some of this stuff in for before. Specifically this. Okay. So we find the memory mapped range of the device. So the PCI card is plugged in. He's got direct access to memory, and he takes like some physical memory and says, this is no longer memory. This is like how these are just mapped to these registers on this device, this physical to card, and you can look at the memory inside the card. So we'll say that the registers start here at the beginning of mapped memory range. This is a function that we implemented back in our like PCI days, where basically you like ask the PCI card for this like there's like configuration registers for every PCI card, and one of those configuration registers will tell you where the memory mapped IO is essentially. And so I guess for each of these guys, we're going to add this to the offsets. We'll say self, or not self, regs, add, reg, nope. What is this guy's type? He's an mmap range. I see. So it's regs start, add this number, but in hex. And then we take this guy and we put him over here as the variable name, but in lowercase. And then we delete the rest of the line. And I think I forgot to record that macro, so we have to do that again. So we say regs start add this in hex. Then we go back, we set this as the variable name, we lowercase it, and we delete the rest of the line. There we go. Okay, So now we have all of our registers, and let's just get their default value. So, let's see what I want to do here. I guess these are going to be like register names. So we'll call them reg. And I guess all of these guys are, we have to set them to like their type. So these are 2222, 2 bytes, 2 bytes, 2 bytes, 2 bytes, 4 byte, 1 byte, 2 bytes, 2 bytes. And I think they said 1 byte. Cool. Which actually probably means that some of these aren't aligned. But we'll see. And what are we going to do here? We're going to say for each of these registers, let's just print out their value. So we'll say info log this guy, and this is just a read volatile. And I think that's fine. Yeah, it looks like that compiles. We're close. We left an E instead of a U somewhere. So it main 281. This just turns into a U. And let's see what we get. Failed to find mmap range. Okay, that's interesting. So that means that when we tried to do our probe here, we're failing here. Let's just double check for UHCI. We'll just put a specific log message in there so that we can diagnose where it came from. Yeah, interesting. So why would that be? Oh. Okay. So it's because this guy's actually not using mmap registers. So to expand on this a little bit, these lines that go to it's kind of, let's fix this diagram a little bit. So this is kind of more like this. We'll erase this memory stuff. We'll come back to this. It looks kind of more like this, where CPU has some memory lines that go to both this like IO port stuff as well as like RAM. Oversimplification, but approximately. And this stuff, you talk to the, like, what happens is when you talk to like IO, you basically like mux these lines and you say like, I'm not actually going to read from memory. I'm going to use that same like set of lines and I'm going to talk to like physical devices. This oversimplification is going to be a problem actually. This is actually called memory controller. We'll call this memory controller, which is connected to RAM. I'll also prefix this by saying this is my mental model and I think it's correct, but I could be wrong. So what happens is with USB 2.0, what we saw was our UHCI controller had this line over here, where his USB host had direct access to both RAM. He had like memory mapped, like he could like write to RAM directly, and he also was directly connected to the memory controller. Basically saying like, hey, you could like talk to me by talking to this specific memory address. And the reason to do that is I think that like the muxing between IO and the memory controller is like maybe slower than if you just like have the memory controller do it itself. But what this guy's saying is instead of this line, it's actually connected like this, where our USB host is connected to like IO ports. And so we can't do the same trick of using memory mapped registers. And so probably what I should be able to do here is I also have this thing that says like find IO base. And this gets like a little bit trickier. So the way we work with this is I think we have like an IO allocator. that basically like enforces that we only ever work with IO ports with a single device from a single spot in code at a time, which is kind of nice for us. So I think here we just pass in IO allocator is an IO allocator. Great. And then in main, we just pass in the allocator like this. Okay. Oh, he wants us to be and mute like this. Cool. Does it still compile? I actually don't know if it will because of mutability problems. This stuff is all wrong now. And let's see if this at least works. So we'll change this from mmap range to IO base, is what we called it. Okay, so we find our IO base, and now we can say, what is the type of this guy? He's a U32, so we'll just say IO allocator. Allocate, what's like my thing here? I say request IO range. And so I have like the base address here, and the length, do I know it? I guess I'll just write something here, but I guess it's probably I'm supposed to know it from the PCI thing. PCI is probably supposed to tell me how many registers there are. But for now, I'll just write 20. I'll say I want 20 bytes, please, and then I'll say failed to allocate IO range. And this would be as U16. I did think that I was supposed to get a range there, but that's okay. And now I can just do... So all of these guys, I'm going to change to say, this is IO range. Oh, fuck. What's the API on this? I'll have to do it once to understand it, and then we'll do the macro shit after. So here we say IO range, and we'll say read 32. Right. Okay. So what we have is like this IO range is a type of IO range, and if I look at my thing here, basically this has like assembly functions to read and write specific values in 32-bit or 8-bit mode. And so it looks like we're probably going to have to add the 16-bit versions of this. So let's just quickly do that. Where's that? So I think I'm going to look at the like out x86 assembly instruction. And he has, if I have AL, AX, and EAX. So if I remember correctly, there are like 3 register modes. There's like 8-bit, 16-bit, and 32-bit. This one's 32-bit. This one's 8-bit. This one's 16-bit. And then there's also like an AH register where that's the high 8 bits of the 16. Like, hold on. I think my register is this big. 32, 0, 16, 8. I think this is AL. I think where A is like register A. I think this is AH. This is AX, I think. And this whole thing is EAX. And so this is saying like, hey, if you just call me with my register argument as AL, I'll give you like the 8-bit mode. If you do it in AX, you'll be giving me the 16-bit mode, and this is the 32-bit mode, right? You're just saying, like, he's figuring out what he wants to write by the parameter. And so here, I can probably just copy-paste these 32-bit functions and call them 16. And here, instead of EAX, I'm just going to take out the E's. Probably. I'm guessing, but We'll see. Cargo check. Does that compile at least? That compiles. The UHCI stuff doesn't. So here I'm going to say IO range dot read 16 at offset 0. That sounds right. And there we go. Okay. So IO range has to be declared as mutable for this to work, because it's like a 2-stage thing, I think. No, I don't know why it's mutable. Maybe just to guarantee single ownership. And now we can do the vim macro to convert these. So we delete the register thing. We convert this into IO range. We say read, and we will fill in the bit type later. We convert this into an IO offset. We delete words. And then now we have the... Oh, fuck. I think I just fucked up the macro. Yeah, okay. So I think now... Yeah, the macro is a little broken, so let me just quickly fix it. You can actually... Oh, man, that's funny. You can just like paste. So these are like the sequence of letters that I wrote in Vim to put into this macro. And I'm just saying like, oh, I know that these 3 characters that I typed will break it, and I can then just fix it. That's pretty funny. That looks right. 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 Okay. And so then I can just replace all these infos with finding the reg and deleting till the end of the line. There we go. Oh, and these can fail. Fuck. So I just go here and I say expect failed to read register. Okay. Okay. Let's take a little look-see again. See if we get something sane. Fuck. Because I didn't allocate enough space, so I'll just change this to 30. Bing, bang, boom. Okay. So now we have, like, things for all of these addresses, and let's see if they match up with what we see in the doc. Command register, 0. Command, 0. Status, default value, 0. Not 0. Interrupt, 0 is 0. So we are kind of seeing... what we saw last time was that we did, if we... how do I say this? The USB controller was not in its default state when we... when we booted our OS, and we could argue that maybe it's because the bootloader is like interacting with USB in some way. And so what we did last time was we reset the CPU, we reset the card before we did anything. And then we reread the registers and we saw something that looked a lot more sane. So let's do the same thing that we did last time where we write the host controller reset value to the command register. And so here we say write 16 at this offset, and we'll just say write this number, where this number should set the reset flag. And then I guess we have to do a sleep again. So let's sleep for like some short amount of time, using the time and the wake up list. We await this. Great. So let's just see if that does something. Uh, maybe? Actually, no. Weirdly, we're seeing the exact same thing. Can I let sleep for longer? Oh, oops, I'm sleeping at the wrong spot. Yeah, thank you. Good catch. Sleep after reset. Whoever said that in chat, you're a genius. Good catch, good catch. It is still not showing the... It's still showing the same values we saw before. So let's try just sleeping for longer. Just to see. Okay, so we saw that there was a long sleep there. We are also still seeing the wrong values. Or like the same values we saw before. Oh, maybe not. FR base add reg. Uh-oh, did I crash? No, I'm back. Yeah, we're back. FR base add reg, was that 0 before? Why is that not even like in here? It might have been 0 the whole time. Okay, let's double check something else. So let's double check where we're getting these, like, this address space from. So when we say find IO base, let's just print line here. Found, or info log, found IO base at I. The idea being like, maybe we're, I think I saw somewhere. I'm recalling that I saw the term bar 4 somewhere. Maybe it was in like the UHCI shit, which I've just lost, I guess. What the fuck? I guess it was here. Yeah. Here, I saw PCI configuration space will find the IO port base address information in bar 4. And so maybe we are not getting it from bar 4. Just maybe. So we'll say info searching for IO base. Let's see what we get. So we say searching for IO base. And then we just don't. What the fuck? Oh, it's because I put the info log after the return. Dumb. Okay, so we did find IO base at 4. So we are looking at the right spot. The fact that that matches this does indicate the right thing. So then the question becomes like, why am I not seeing these registers match what I expect them to be? And it could be because the reset is not working correctly. Seems possible. Or sorry, working correctly. It could be that I'm just like I just randomly started typing, right? Like maybe what I typed is like fucking stupid. So let's maybe read this and see if we can find out how to reset this guy. Does someone tell me like none of this says like initialization in the table of contents. Wow. So we could just read this a little closer. When this bit is set, the host controller module resets into eternal timers, counters, state machines, etc. to their initial value. Any transaction currently in progress on USB is immediately terminated. This bit is reset by the host controller when the reset process is complete. Okay, so we could say, is there anything else in here that seems sketchy that like we would need to do? No. What's the run stop bit? It doesn't look like that important. So it looks like I should be able to write 1 and then read till it says 0. And that should be when it's finished. And what we might see is we might see it infinite loop, or we might see it do the right thing. So I'll just double check that we're writing to the right register. Command offset is 0, so we should be writing to the right thing. This is a 2-byte register, so let's just make sure that I'm doing reads, 16-bit reads and writes. Great. 16-bit reads. So now I should just be able to say loop while IO range read 16 at IO offset 0. And we'll say get bit 1. So while that's set, it's resetting. And we can delete the sleep. And I also have to like use my utility class for bit manipulation to get that function to exist. Hello? Where did my loop go? Didn't I just... Oh, here. Oh, I have to unwrap this. There we go. There we go. So now we should see a little bit of a delay in there. I guess the problem is if it doesn't ever change, we wouldn't see this happen, right? We're kind of like probably immediately returning. To enter software debug mode. Does this guy talk about like a reset? No. No, he does not. HC reset. Is there anywhere... This is the only time it's mentioned. I feel like I'm missing something. Let's just double check here. So we have status reg set to 32. And his saying his default value is 0. So what is this 32? So the only thing that's wrong here is that we have this HC halted thing said. I wonder if host controller bit sets this bit to 1 after it has stopped executing as a result of the run stop bit being set to 0. So what happens if I reset this with a 1? Right? We set the run stop bit to 1, we should see this guy change behavior. No. But we can just maybe read the rest and see if they are at least sane. Interrupt reg, I think we saw set to 0. FR num reg is default value should be 0, so why would it not be? 102, baby. What is this guy? What is he at all? The register reflects the count value of the internal frame number counter. The register must be written as a word. I wonder if it's like something like, this register cannot be written unless the host controller is in the stop state. Any write to this register while the run stop bit is set is ignored. So I wonder if we could prove to ourselves, we could try writing to it. It should fail, and then we could try setting the run stop bit, and then writing it again, maybe, and see if that gives us anything. But let's just keep going and see if anything else makes sense. Start of frame, so at 0xch, soft mod, we should see this at 40, which we probably don't. 64. Oh wait, no we do. 48 to 64, so that's right. And port status, let's log these as hex. Just because that's easier to correlate. We just dropped some X's in here. Drop some X's in. So this is right, the 40. And then this guy says that his first thing should be 80. Both of these guys should be 80. Okay. So it could be that maybe the port status is increasing compared to what we would normally expect because something's plugged in. So maybe like immediately we plug in the USB controller, we reset it, and it goes to its default values, but then it immediately goes farther than its default values because like we've plugged something in. So I wonder if I just like nuke these other devices, the tablet that's plugged in, if we start to see something different. Okay. So the fact that's a really good sign. That's a really good sign. Yeah, the fact that these dropped, so the frame num is actually gone up, which is interesting. But the port status register has changed. So I think that that's a very, very good indication that we are at least looking at the right thing, right? As soon as I took something out of port 1, we saw the port status reg change. And we saw it change from 8.3 to 8.0. And so let's see what 8.3 would be. It would be devices present, and there would be a change in status. So that's pretty sick. And I guess what we should do, what we can also prove, is if we switch the ports from bus 0 to bus 1, we should see the other one change. So before we had it in port status 1, and now if we run, we should see it in port status 2. Fuck. How do I change this again? QEMU USB bus.0 port equals 1. So here we see this is port 1. And can I change this to port equals 2 maybe? Maybe they're 1 indexed. Let's go! That's 6. So what we just saw was that before we were seeing the status register change in number 1, now we're seeing it change in number 2. Wonderful. So I think that that's a good enough proof for me that our IOS, like, we're at least looking at the right spots. And was that a 16-bit port? If that's a 16-bit port, that also proves that our read and write 16 implementations are right, which it is. Fuck yes. Okay, so that proves a lot. And I guess next up is to try to actually do something of any value at all. Which I will do after I go to the washroom. Give me like 2 minutes. Be right back. Okay, sorry. Hate to do this. But I had to cut some of the video. Well, I had to is strong. I decided to cut some of the video because there was I kind of got to the point where I was just scrolling docs and slowly reading them out loud, and I think that's not very interesting. So I'll just filming the outro separately. Pretty happy with the progress we made today. We managed to talk to the UHCI controller. And I think that I'm going to do some more reading off screen and just try to catch up and figure out what are the next steps. I don't have no idea what to do next, essentially. So I'm going to do some reading off screen, come back tomorrow with fresh eyes, and hopefully have some form of a plan on how to get going next. If you want to catch me live, I stream most days at 1 or 2 o'clock Pacific time. And if you want to catch up, that's, I'll be posting videos here most days. Yeah, thanks for watching. Catch you on the next one. Bye.